All right, now we're going to fill out our learning card on compound probabilities. Now, you could also look at this as if it were um, the multiplication rule and the addition rule. So that's another way to look at this. But with compound probabilities, we need to ask ourselves if we have independent events or dependent events. Now, the difference between independent and dependent is the fact that when you have events that are independent of each other, the probability of one does not change when the other event occurs. So that's an important concept to remember. So once again, just to review there, events that are independent, or I should say events are independent if the probability of one does not change when the other event occurs. So we're going to look at, first of all, rolling a die and spinning a spinner. These two events are independent of each other because the probability of rolling, let's say the probability of rolling a 3 and the probability of spinning a red, let's just say that these other 3 spots are different colors. Those are independent of each other. If I spin a red, it's not going to change the probability of rolling a 3. If I spin a 3, it's not going to change the probability of rolling a red. So we say that those two events are independent. So what if I wanted to know this? What if I want to know the probability of rolling a 3 and rolling and spinning a red? Well, because they are independent of each other, I can just multiply those two probabilities together. So the probability of rolling a 3 and spinning a red when they are independent is the probability of rolling a 3 times the probability of spinning a red. We call this, excuse me, we call this an intersection. When we have an and problem, it's an intersection problem. And when you see the word and, you should think multiplication. So if we continue this out and go ahead and find the probabilities, the probability of rolling a 3 and spinning a red is equal to the probability of rolling a 3 times the probability of spinning red. And in this case, it would be 1 out of 6 for the probability of rolling a 3 and 1 out of 4 for the probability of spinning red. So 1 out of 6 times 1/4 is 1 out of 24. So there's an example of an intersection problem, a multiplication rule problem with the word and when we have independent events. Well, what if we had an or problem? Well, whenever you see the word or in a probability problem, that's a union problem, the union of two events. And when you see that, you should think addition. So as we go through this, what we really want to see now is what is the probability of rolling a 3 or spinning a red? Well, the probability of rolling a 3 or spinning a red is equal to the probability of rolling a 3 plus the probability of spinning a red minus the probability of rolling a 3 and spinning a red. I should change this to and. There we go. So what happens when we look at the union of two events is that we add the two events together, but when we add the two probabilities together, there's a possibility that there's some overlap there. So we don't want to add the overlap twice. So in order to avoid that, what we end up doing is we subtract away the overlap. So the probability of rolling a 3 or spinning a red is equal to the probability of rolling a 3 plus the probability of spinning a red minus the probability of rolling a 3 and spinning a red, because that comes up more than once. So when we look at that probability, the probability of rolling a 3 is 1 out of 6. The probability of spinning a red is 1 out of 4, minus the probability of both happening, and we figured that out in the previous example. And then when you do all the math here, because of algebra, this is 9/24. So our probability would be 9 out of 24. Now, some people ask me, should we write our answer as a fraction or a decimal or a percent? Any one of them is okay. And even when you have a fraction, you don't necessarily have to reduce it. 9/24 does reduce, but if you leave your answer as 9/24, that's okay as well. Well, there's two examples of independent events. What about dependent events? How do we do an intersection problem and a union problem if we have dependent events? Well, first of all, let's set up a scenario. So in this scenario, let's go ahead and compare playing football versus size. So I've got a little two-way table here, a little contingency table, and we're just going to classify people as big and small. Yes, they are playing football, or no, they are not playing football. Don't read into this. We just need an example, and this is the example we're going to use. So we have, of the big people, we have 20 that play football and 10 that don't. People that we classify as being small, we have 4 people that play football and 25 that do not. And so I went ahead and added our marginal distributions here as well. So yes, there are 24 people that play football, 35 people that do not play football. There are 30 people that we classify as big, and there are 29 people that we classify as small. So now, how do we apply this to our intersection or and problems and our union or problems? Well, if the two events were independent of each other, being big and playing football, then we could look at it like this. The probability of being big and playing football would be the probability of being big times the probability of, yes, you play football. Well, the probability of being big would be 30 out of 59, which is the total amount of people, and the probability of playing football would be 24 out of 59. So if we multiplied that out, that would be 720 out of 3,481, which is about 21% or 20.7%. But if we look at this two-way table, this contingency table, we can see that they are not independent. And here's the reason why. If we highlight and look at this question again, what is the probability of being big and playing football? Well, what we have is this right here. The probability of being big and playing football, there are 20 people that are both big and, yes, they play football, would be 20 out of the grand total, which is 59. So what is that equal to? So if they were dependent on each other, then the probability of being big and, yes, to playing football would be 20 out of 59, which is 34% or 0.34. We can see that these two probabilities are not equal to each other. So which one is it? If they were independent, then we could go with this. If they're not independent, or if they are dependent, then the probability is this. So in reality, what we have right here on the top is not correct. So let's cross this out. They are dependent on each other. And the reason why I know that is because of the two-way table that I have up here. Okay? Well, what if we have an or problem? What if we have the probability of being big or the probability of playing football? That would look like this. The probability of being big or saying yes to football would be equal to the probability of being big plus the probability of yes to football minus the probability of being big and saying yes to football. Okay, well, let's find those probabilities. And that would be this. The probability of being classified as big is 30 out of 59, plus the probability of saying yes to football, you play football, 24 out of 59, minus the probability of both, big and yes, which we just found right here was 0.34 or 20 out of 59. That leads us to 34 out of 59, which is about 0.576 or 57.6%. So there's 4 examples of how to handle and problems and or problems, or intersection and union problems, if we have independent events compared to dependent events. Hopefully you've learned a little bit about probability and the difference between independence and dependence, and I hope you have fun in your stats.